Chapter 8, Section 3. A tool that's often used when dealing with population distributions is an average value. In this section, we will cover a variation of two familiar methods that we use to compute averages. We're going to look at the data and we're going to find what's called the mean and the median. We'll also take a look at the concept of normal distribution and observe how this relates to populations. We'll start by talking about the median. For a median, we're looking for the value for which half the data is to the left of that value and half the data is to the right of that value. So in order to do that, we get a general form that says the integral from negative infinity to capital T of our PDF equals 0.5. Now again, this just means wherever our PDF starts up to the value of t. So if our PDF is only defined between, say, 0 and 50, we would start from 0. But this negative infinity allows us to start at any value. So wherever your PDF is defined, that's where we start. Similarly, if you have the CDF, or the cumulative distribution function, we can set that equal to 0.5 and solve. These mean the same exact thing. In both equations, again, t is going to represent the value for which half the population has x values that are less than t, and half the population has x values that are greater than t. Let's look at an example. Let t be the amount of time it takes for a slice of bread to digest. This is represented by the density function graph below, and by p of t equals 0.05 minus 0.00125 t. So we have the graph, and we want to answer the following questions. How long does it take for 100% of the slice of bread to be digested? B. Do you expect the median time to be less than, equal to, or greater than 20 minutes? C. Find the median time needed to digest the slice of bread. So let's start with A and B. Part A. How long to digest 100% of the bread? Well, we know that it's going to be no more than 40 minutes, because at 40 minutes, the area under the graph is 1, or 100%. That's how PDFs are defined. So here we can see that our time options are 0 to 40, 40 being the upper bound. For part B, is the median time less than, equal to, or greater than 20 minutes? Now, if you look at 20, and remember that the median is when half the population is less than a number and half is greater than. If we look to the left and the right, to the left there's a lot more area under the curve than to the right. So what that tells us is that our actual median should be to the left of 20, because we need to find the point where the areas are equal. So since it's greater than, we move towards the greater than side to figure out about where our median is going to be. So we expect our median time to be less than 20 minutes. Now, for part C, we want to actually calculate the median time needed to digest this bread. So again, our general form is going to be the integral from negative infinity to t of our density function. As I said before, this negative infinity actually is going to be whatever our lower bound is. Here, we're defined from 0 to 40. So that means instead of negative infinity, we're going to go from 0 to t, because 0 is where we actually start our defined PDF. So we want to integrate from 0 to t our PDF, and we want to set it equal to 0.5. Okay, so our PDF here was 0.05 minus 0.00125 t. We're integrating from 0 to t, and we want to know when does that equal 0.5. So when we integrate, we get an antiderivative of 0.05 t minus 0.00625 t squared. We're going from 0 to t. So when we plug in capital T, we get 0.05 t minus 0.00625 t squared. Then we'll have minus, and when we plug in 0, we just get 0. So then we want to know, when does that equal 0.5? So what we want to do is we want to get everything onto one side of the equation. So if we add the 0.00625 t squared to the right, and then we subtract the 0.05 t to the right, we get 0.00625 t squared minus 0.05 t plus 0.5 equals 0. Now the reason we do this is because now we have a nice quadratic equation, and we can solve for the roots by using the quadratic equation. If it's been a while, hopefully it sounds familiar, the quadratic equation is the opposite of b, which is the number in front of the middle term, plus or minus the square root of b squared minus 4 times a, the coefficient in front of the squared term, times c, which is our standalone number, all divided by 2 times a. Using the quadratic equation, we get roots of t equals 11.72 or t equals 68.28. Now remember, our PDF was only defined for t's between 0 and 40, which means that of the two solutions, the one we want is 11.72. So here, our median is 11.72. And again, we expected it to be less than 20, and it is. So whenever you're calculating a median, you want to integrate from your starting point to t, your PDF, set it equal to 0.5, and solve. Now let's talk a little bit about the mean. The mean is the average value of a function. It's the same mean you would think of when you talk about averages of grades and things of that sort. So if we were to add up all the values of a population and divide by the size of the population, that gives us the mean. How does that work with integrals? Well, it turns out that the mean value of a function is going to be defined by the area under the curve from negative infinity to infinity of x times p of x, our PDF. So whatever your variable is, we're multiplying by that one time, and that'll calculate the mean for us. Let's look at some examples. So suppose that our PDF is 2.38 e to the negative 0.122t for t between 0 and 40. And we want to find the mean value of the function. So again, our general form is going to be the integral from negative infinity to infinity. Since we're using t's here, it'll be t times our PDF dt. Well, here we know our integral is not defined from negative infinity to infinity. As a matter of fact, t is bounded by 0 and 40. So that's what we put on our integral. So we have the integral from 0 to 40 of t times the PDF, which was 2.38 e to the negative 0.122t dt. This is a definite integral, and we can just plug that right into our calculator. When you plug that in, that's going to give us a mean value of 152.76. So again, when we're finding the mean, we're just doing the variable that we're using, here it's t, sometimes it's x, times the PDF, and we integrate over the bounds for which our variable is defined. And that'll give us the mean value of the function. Okay, let's do both now so we can again see the difference between the two. So let p of t equal 0.1 e to the negative 0.1 t be the density function of waiting time at a bus stop, with t in minutes, where t is going to be between 0 and 60 minutes. We want to find the mean and the median. Okay, well we just did the mean, so let's do it again. The mean, again, we're going to plug in the bounds for which our variable is defined, so 0 to 60. Then we're going to take our PDF, 0.1 e to the negative 0.1 t, and multiply it by our variable of t. Once we have it all set up, we'll plug that right into our calculator, and we'll get a mean waiting time of 9.826 minutes. What about the median? Well, again, the median is going to be the integral from negative infinity to t of our PDF. We want to set that equal to 0.5. To find our median, it may take a while, so we'll give an estimate of where the median is. So let's take the antiderivative and use the shorthand method of the fundamental theorem to solve. So again, since we're defined from 0 to 60, instead of negative infinity, we start at 0. So now, we take the antiderivative of our function, which will give us 0.1 e to the negative 0.1 t divided by negative 0.01. The 0.1's cancel, so we have negative e to the negative 0.01 t plus c. But now, let's involve our bounds. Using the shorthand method, we can eliminate c because we're now plugging in our bounds. So we have negative e to the negative 0.01 t from 0 to capital T. We plug in our capital T as our upper bound, minus, and then we plug in 0 as our lower bound, Notice here that we're subtracting a negative, so those will cancel. We're going to end up with e to the 0. Anything to the 0 is just 1. So we have negative e to the negative 0.1t plus 1. Now we want to know, when does that equal 0.5? So we set our equation equal to 0.5 to solve for t. So our CDF, now that we've calculated the antiderivative, is negative e to the negative 0.1t plus 1 equals 0.5. We can subtract 1 from both sides, so we get negative e to the negative 0.01t equals negative 0.5. We don't want that negative in there, so we multiply both sides by negative 1, and that'll give us e to the negative 0.1t equals 0.5. Now to get that t down, we take natural logs of both sides. When we take the natural log on the left, the power comes down out front, so we have negative 0.1t times the natural log of e equals the natural log of 0.5. Remember, the natural log of e is just 1, so that goes away. So that leaves us with negative 0.1t equals the natural log of 0.5, which tells us that t will finally equal the natural log of 0.5 divided by negative 0.1. If you do that in your calculator, we get that t equals 6.93. So the median waiting time here is 6.93. So again, with the median, we're setting it equal to 0.5, and with the mean, we're multiplying by that extra variable. Okay, now let's talk about the normal distribution. So when we talk about data, sometimes it's distributed in such a way that it forms what's called a bell-shaped curve, which means there's some sort of middle ground where most of the data is gathered. As you move away from that, it slowly flattens out, creating this bell shape. And that's called the normal distribution. And they're quite commonly used to model real phenomenon. So, exam grades are a great example. If a large number of test scores are recorded and graphed, the majority of the grades will typically be 75%. We know this is the class average. Mathematicians, we call this the mean, and it's often written with this letter mu, which is the Greek form of the letter m. And usually low and high grades are found less frequently, and so we call these the standard deviation. It's how far away you are from the mean, and that's represented by this Greek symbol right over here. Okay? So now, the general form for a normal distribution density function looks like this, okay? It's a little bit more complex than what we're used to, but it's nothing that we can't handle. So we have 1 over, and then here's it's called sigma, square root of 2 pi e raised to the power of negative, parenthesis, x minus mu, the mean, squared, all divided by 2 sigma squared. And this is what the data looks like when it's graphed. This is what our PDF function looks like. That's what we're referring to with the bell-shaped curve. Now that we've talked about the mean, we can sort of relate that. And the standard deviation is more just an idea of how far you can move away from the mean before you drop off towards 0. So if we want to talk about data distributed normally, we can find out how it's distributed by integrating this PDF. So let's do an example to see how we put this into play. So Colorado ski officials review their annual data on snowfall in preparation for the upcoming winter ski season. They graph their findings using a normal distribution curve and find that their mean snowfall is 15 inches with a standard deviation of 1. We want to compute the fraction of years with snowfall between 13 and 17 inches, 12 and 18 inches, and 14 and 16 inches. Okay, so when we're looking to look between two numbers, that's going to tell us, like our x values or t values, what bounds to integrate over. So we're doing 3 different problems here, so let's start with A. So remember, mu is 15, sigma is 1, and our general PDF looks like this. So if we're calculating between 13 and 17 inches, we're plugging in a 1 wherever we see the sigma, which will be here and up here, and we're plugging in a 15 for mu, which is up in the power of e. Other than that, everything else is numbers. Pi is a number just like e. So very, very carefully, with parentheses, we're going to plug this into the calculator. Now when you do this, you need to be very careful that all your parentheses are correct, or else you'll get errors. So very carefully, when you plug this in, you should get that it equals 0.95, which is 95%. So 95% of the time, we're going to get between 13 and 17 inches of snow. Now, part B, we want to know between 12 and 18 inches. Now, if 13 to 17 is 95%, and we've expanded our interval here, 12 to 18, it's a bigger interval, we expect that's going to be a higher percentage because now we've included more numbers. So here, we integrate from 12 to 18. Again, sigma is 1, so we plug that in everywhere we see the sigma. Mu is 15, that goes in up here. Very carefully, we plug this into our calculator, and we get 0.997. So 99.7% of the time, there's between 12 and 18 inches of snow. Now for the last one, we're going to look between 14 and 16 inches. Now that's a smaller interval than 13 to 17 because now there's an inch shaved off either side. So we expect it to be less than 95%. So here we integrate from 14 to 16. Again, our mu and sigma don't change. We very carefully plug this in to our calculator and we get 68%. Which is what we expect because we shrunk the interval. So with normal distributions, you're always using this same PDF. So whenever you see a normal curve, you start here, and you should be given your mean and standard deviation. You'll be plugging that in, and then your bounds will be defined by the situation at hand.